What if I told you that tomorrow morning gravity might decide to work backwards? What if the speed of light suddenly changed its mind and started moving at the pace of a lazy Sunday stroll? What if the electromagnetic force that holds your atoms together just quit? Your coffee would float toward the ceiling. Your phone would phase through your hand like a ghost. And honestly, you wouldn't be around long enough to worry about any of it because the atoms in your body would simply stop cooperating with each other. It sounds absurd, maybe even impossible. But here's the thing that should genuinely terrify you. There is absolutely no obvious reason why the universe has to follow consistent rules at all. Think about it. We live in a cosmos that has operated like the most reliable clockwork mechanism imaginable for 13.8 billion years straight, never missing a beat, never changing the fundamental equations that govern everything from the smallest quantum particles to the largest galactic superclusters. The same mathematical relationships that describe how a pencil falls from your desk also govern the intricate dance of binary neutron stars spiraling into each other millions of light years away. The same quantum mechanical principles that make your smartphone work also determine how massive stars forge carbon, oxygen, and iron in their nuclear furnaces before exploding and seeding space with the elements that eventually became you. Our story begins not in modern laboratories filled with particle accelerators and quantum computers, but in the ancient world, where some of the most brilliant minds in human history first dared to ask a question that would revolutionize our understanding of existence itself. Is there some underlying order to the apparent chaos of the natural world? This wasn't just idle philosophical speculation. These ancient thinkers were grappling with the same fundamental mystery that puzzles us today, and their insights would lay the groundwork for everything we now understand about the consistency of natural laws. To truly appreciate why the universe follows consistent rules, we need to understand how humans first discovered that such rules might exist at all. The journey begins in the 6th century BCE in the bustling Greek city of Miletus, located in what is now modern-day Turkey, where a merchant and philosopher named Thales was making observations that would change the course of human thought forever. Thales is often called the first scientist, not because he had access to sophisticated instruments or mathematical techniques, but because he was among the first people in recorded history to suggest that natural phenomena could be explained through natural causes rather than the whims of gods. This might seem obvious to us now, but in Thales' time, it was revolutionary. When earthquakes shook the ground, most people assumed Poseidon was angry. When lightning split the sky, Zeus was hurling thunderbolts. When the seasons changed, Demeter was mourning or rejoicing for her daughter Persephone. Thales looked at these same phenomena and proposed something radically different. What if there were consistent, discoverable principles underlying all of these changes? Thales's most famous proposition was that everything in the universe was fundamentally made of water in different forms and states. While this might seem naive to modern ears, the profound insight wasn't about water specifically, but about the concept of underlying unity. Thales was suggesting that beneath the bewildering diversity of natural phenomena, solid rocks, flowing rivers, burning fires, moving air, there might be a single, consistent substance that takes on different forms under different conditions. He was proposing that the universe has a fundamental consistency at its deepest level, that all the apparent variety and change we observe are really just different manifestations of the same underlying reality operating according to consistent principles. This was the first recorded attempt in Western thought to find universal rules that could explain the behavior of everything in the natural world. But Thales was just the beginning. His intellectual descendants pushed this idea much further, and none more so than Pythagoras of Samos, who lived in the late 6th and early 5th centuries before Common Era. Pythagoras and his followers made a discovery that still sends chills down the spines of physicists and mathematicians today. The universe appears to be fundamentally mathematical in nature. This revelation came through their investigations of musical harmony, where they discovered that pleasing musical intervals correspond to simple mathematical ratios. When a string is plucked, it produces a certain note. When half the string is plucked, it produces a note exactly 1 octave higher. When 2/3 of the string is plucked, it produces a perfect fifth. These weren't arbitrary relationships. They were precise mathematical ratios that seemed to govern something as subjective and aesthetic as musical beauty. The Pythagoreans extrapolated this discovery into a comprehensive worldview that they summarized in the phrase, all is number. They believed that mathematical relationships weren't just useful tools for describing natural phenomena. They were the fundamental reality underlying all existence. The physical world, with all its complexity and apparent chaos, was really just mathematics expressing itself through space and time. This wasn't merely metaphorical. The Pythagoreans believed that geometric shapes, numerical relationships, and mathematical harmonies were more real than the physical objects we could see and touch. They developed the concept of the music of the spheres, the idea that the planets and stars moved through space according to mathematical harmonies, creating a cosmic symphony that most humans couldn't hear, but that revealed the mathematical structure underlying all of reality. This Pythagorean insight that mathematics might be the fundamental language of nature was so profound that it continues to astonish scientists today. When modern physicists write down equations describing quantum mechanics or general relativity, they're essentially following the same intuition that struck the Pythagoreans 2,500 years ago. The universe seems to be written in mathematical code. And if we can crack that code, we can understand the consistent rules that govern everything from subatomic particles to cosmic superclusters. The fact that this ancient insight has proven so prescient suggests that the Pythagoreans stumbled onto something genuinely fundamental about the nature of reality. The next major leap in understanding cosmic consistency came from Heraclitus of Ephesus, who lived around 535 to 475 BCE and is famous for his doctrine that you cannot step into the same river twice. But Heraclitus wasn't advocating for chaos or randomness. Quite the opposite. He was pointing out that beneath the constant change and flux that characterizes our everyday experience, there must be some deeper principle that governs how things change. The river is never the same because new water is always flowing through it, but the river itself, its banks, its course, its essential character, remains constant. This led Heraclitus to propose the concept of logos, a universal principle of order and knowledge that governs all change and transformation in the universe. According to Heraclitus, the logos was like a cosmic law that ensured that all the apparent chaos and change in the world followed consistent patterns. Fire transforms into air into water, water into earth, and earth back into fire. But these transformations don't happen randomly. They follow the logos, a rational principle that maintains cosmic harmony even in the midst of constant change. This was perhaps the first explicit articulation of the idea that the universe operates according to consistent rules that remain constant even as everything else changes. The logos wasn't just a description of how things happen to behave, it was a fundamental principle that determines how things must behave. But it was Plato, writing in the 4th century BCE, who developed the most sophisticated and influential ancient theory about why the universe follows consistent rules. Plato's theory of forms proposed that our physical world is just a shadow or imperfect reflection of a perfect, eternal realm of mathematical and geometric ideals. In this realm of forms, there exist perfect triangles, perfect circles, perfect justice, perfect beauty, and perfect mathematical relationships. Everything we observe in the physical world is an approximation of these perfect forms, which is why we can recognize triangular shapes even though no physical triangle is perfectly geometric, and why mathematical relationships discovered through pure thought turn out to describe physical phenomena with such precision. According to Plato's theory, the universe follows consistent rules, because these rules reflect the perfect, eternal mathematical relationships that exist in the realm of forms. Physical laws aren't arbitrary. They're shadows cast by perfect mathematical truths. This explains why mathematics, developed through pure abstract reasoning, turns out to be so unreasonably effective at describing and predicting natural phenomena. We're not imposing mathematical structure onto a chaotic world. We're discovering the mathematical structure that was always there, the eternal, geometric, and numerical relationships that give the physical world whatever consistency and rationality it possesses. Plato illustrated this with his famous allegory of the cave, where prisoners chained in a cave mistake shadows on the wall for reality itself. According to Plato, we're all like those prisoners. What we call physical reality is just shadows cast by the perfect mathematical forms. The consistent rules we observe in nature are reflections of the perfect logical and mathematical consistency that characterizes the realm of forms. This means that the universe follows consistent rules not by accident, but by necessity. It couldn't be otherwise, because inconsistency and irrationality cannot exist in the perfect realm that serves as the template for physical reality. Aristotle, Plato's student, developed a somewhat different but equally influential approach to understanding natural consistency. Where Plato emphasized eternal mathematical forms existing outside of space and time, Aristotle focused on the inherent natures and tendencies of physical objects themselves. According to Aristotle, everything in the universe has a specific nature that determines how it will behave under various circumstances. A stone falls toward the earth not because of some external mathematical law, but because it's in the nature of stones to move toward their natural place at the center of the universe. Fire rises because it's in the nature of fire to move toward its natural place in the celestial sphere. This might sound primitive compared to our modern understanding of gravity and thermodynamics, but Aristotle's insight was actually quite sophisticated. He was proposing that consistent rules emerge from the inherent properties of matter and energy themselves. Objects don't follow external laws imposed from outside. They express their own internal natures in predictable ways. This anticipates modern ideas about how physical laws might emerge from the fundamental properties of space, time, matter, and energy, rather than being imposed on them from some external source. Aristotle also developed the first systematic approach to understanding causation, identifying four different types of causes that work together to produce natural phenomena. The material cause is what something is made of. The formal cause is its structure or pattern. The efficient cause is what brings it about. The final cause is its purpose or end goal. This fourfold analysis of causation was Aristotle's attempt to understand how consistent rules could emerge from the complex interactions between matter, form, energy, and purpose. Every natural phenomenon results from these four causes working together in predictable ways, which is why we can discover consistent patterns in natural behavior. Perhaps most importantly, Aristotle argued that the universe must be eternal and unchanging in its fundamental structure, even though individual objects within it are constantly changing. The overall cosmic order, the arrangement of the celestial spheres, the fundamental natures of different types of matter, the basic principles of motion and change, remains constant throughout time. This cosmic stability is what makes it possible for natural phenomena to follow consistent rules. If the fundamental structure of the universe were constantly changing, then there would be no stable foundation for consistent natural laws. The Greek atomists, led by Democritus in the 5th century BCE, offered yet another perspective on cosmic consistency. They proposed that all of reality consists of tiny, indivisible particles called atoms moving through empty space according to simple, consistent rules. Different types of atoms, with different shapes and sizes, combine in different ways to create the rich variety of natural phenomena we observe. But underneath all this variety, there are just atoms and void, interacting according to purely mechanical principles. This atomistic vision was remarkably prescient, anticipating modern atomic theory by more than 2 millennia. But for our purposes, the most important insight of the atomists was their recognition that complex, apparently rule-governed behavior could emerge from simple, consistent interactions between fundamental components. You don't need to invoke gods, eternal forms, or inherent purposes to explain why nature follows consistent patterns. You just need simple rules governing simple components, and complex consistency emerges automatically from the countless interactions between these components over time. The Stoic philosophers, who developed their school in the 3rd century BCE, synthesized many of these earlier insights into a comprehensive worldview that emphasized the rational, law-governed nature of the universe. According to the Stoics, the universe is pervaded by logos, a rational principle that ensures that everything happens according to reasonable, discoverable laws. This isn't just a human projection onto an indifferent cosmos. It's an objective feature of reality itself. The universe is literally rational, organized according to principles that human reason can discover and understand. The Stoics believed that understanding these natural laws was the key to living a good life. By aligning our behavior with the rational structure of the universe, we can achieve peace and happiness even in the face of circumstances beyond our control. This represents perhaps the first systematic attempt to derive ethical principles from our understanding of natural law, an idea that would later influence both Christian theology and modern scientific humanism. What emerges from this survey of ancient Greek thought is a remarkably sophisticated understanding of the central questions that still puzzle us today. Why does the universe follow consistent rules rather than behaving chaotically? The Greeks offered several possible answers. Because mathematical relationships are fundamental to reality itself, Pythagoras and Plato. Because natural objects have inherent natures that express themselves predictably, Aristotle. Because simple mechanical interactions between fundamental components generate complex consistent behavior, the atomists. Or because the universe is pervaded by a rational principle that ensures logical consistency, Heraclitus and the Stoics. Remarkably, all of these ancient insights remain relevant to contemporary discussions in physics and philosophy. Modern physicists still debate whether mathematical relationships are discovered or invented, whether physical laws emerge from the properties of matter and space-time, or are imposed from some deeper level of reality, whether complex behavior emerges from simple rules or requires fundamental complexity, and whether the universe is inherently rational or merely appears so to rational observers. The questions that puzzled ancient Greek philosophers continue to puzzle us today, which suggests that they identified something genuinely fundamental about the mysterious relationship between human reason and cosmic order. The Greeks established the foundational insight that would drive all subsequent scientific inquiry. The natural world, despite its apparent complexity and constant change, operates according to consistent, discoverable principles that human minds can understand through careful observation and logical reasoning. This wasn't self-evident. It was a revolutionary discovery that had to be made through centuries of careful thought and observation. Without this ancient Greek insight that the universe might be fundamentally rational and law-governed, the entire scientific enterprise would have been impossible. The intellectual revolution that began with the ancient Greeks lay dormant for over a millennium, buried under the weight of medieval scholasticism and religious dogma that prioritized divine revelation over empirical observation. But in the late Renaissance, something extraordinary happened that would forever change humanity's relationship with the cosmos. A handful of brilliant minds began to realize that the Greek intuition about mathematical order in nature wasn't just philosophical speculation. It could be tested, measured, and proven through careful experimentation and mathematical analysis. This marked the birth of what we now call physical laws. Precise, quantitative descriptions of how the universe actually behaves, expressed in the language of mathematics and verified through rigorous observation. The transformation began with Galileo Galilei, whose revolutionary approach to understanding nature would establish the template for all future scientific inquiry. Galileo's genius wasn't primarily in making new observations, though his telescopic discoveries were certainly groundbreaking. His true revolutionary insight was methodological. He realized that the book of nature was written in mathematical language, and that human beings could learn to read this language through carefully designed experiments that isolated specific natural phenomena and subjected them to quantitative analysis. Where ancient and medieval thinkers had relied primarily on logical reasoning from first principles, Galileo insisted that nature herself must be the final arbiter of truth through empirical testing of mathematical hypotheses. Galileo's approach can be seen most clearly in his analysis of falling objects, which demolished over 1,000 years of Aristotelian physics in a single stroke. Aristotle had taught that heavy objects fall faster than light objects because it's in their nature to seek their natural place more urgently. This seemed intuitively reasonable and had been accepted without question for centuries. But Galileo approached the problem mathematically, asking not what objects ought to do according to their supposed natures, but what they actually do when subjected to careful measurement. Through his famous experiments with inclined planes, he discovered that all objects, regardless of their weight or composition, accelerate at exactly the same rate when falling in a vacuum. But Galileo's most profound insight wasn't just that objects fall at a constant acceleration. It was that this acceleration could be described with mathematical precision. He showed that the distance fallen by any object is proportional to the square of the time elapsed. D equals 1/2 gt squared. This wasn't just a useful approximation or a rough description. It was an exact mathematical relationship that held true for every falling object in every circumstance. For the first time in human history, someone had demonstrated that a natural phenomenon could be captured completely in a mathematical equation that made precise, testable predictions about future observations. This discovery revealed something absolutely astonishing about the universe. Beneath the rich complexity of natural phenomena lay simple, elegant mathematical relationships that remained constant across all of space and time. The same equation that described a stone dropping from Galileo's hand also described the motion of projectiles, the swing of pendulums, and even the orbits of planets around the sun. The universe wasn't just orderly in some vague philosophical sense. It was mathematically precise, operating according to exact quantitative rules that human minds could discover and understand. Galileo's mathematical approach to nature reached its full flowering in his analysis of motion, where he demonstrated that the complex trajectories of projectiles could be understood as the combination of two simpler motions: uniform horizontal motion and uniformly accelerated vertical motion. By breaking down complex phenomena into simpler mathematical components, Galileo showed that nature's apparent complexity often masks underlying simplicity. This reductionist approach, the idea that complex systems can be understood by analyzing their simpler parts, would become one of the fundamental strategies of all subsequent science. The implications of Galileo's work extended far beyond physics. If natural phenomena could be described with mathematical precision, then human beings possessed a tool for understanding and predicting natural behavior that was potentially unlimited in its scope and power. Mathematics wasn't just a useful human invention for keeping track of quantities. It was the actual language in which natural laws were written. This suggested that the human mind and the structure of the universe were somehow perfectly matched to each other, that our capacity for mathematical reasoning had evolved specifically to unlock the mathematical secrets of the cosmos. But it was Isaac Newton who transformed Galileo's insights into a complete mathematical description of how the universe operates, creating what we now recognize as the first truly universal physical laws. Newton's achievement was so monumental that it's difficult for us to fully appreciate how radical it was in its historical context. Before Newton, people assumed that terrestrial and celestial phenomena operated according to completely different principles. The heavens were perfect, eternal, and divine, while the earthly realm was corrupt, changeable, and mundane. The idea that the same mathematical laws might govern both domains was not just scientifically revolutionary, it was theologically and philosophically shocking. Newton's breakthrough came through his recognition that the force responsible for making objects fall toward the earth was identical to the force responsible for keeping the moon in orbit around the earth and the planets in orbit around the sun. This wasn't just a clever analogy or a useful approximation. It was literally the same force, operating according to exactly the same mathematical relationship in both terrestrial and celestial contexts. The gravitational force between any two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. F equals g m sub 1 m sub 2 divided by r squared. This single equation described the fall of an apple, the orbit of the moon, the motion of comets, the behavior of tides, and the dynamics of entire solar systems. The universality of Newton's law of gravitation was breathtaking in its scope and precision. It meant that the same mathematical relationship that could predict exactly when and where to find Jupiter's moons also determined how fast a cannonball would travel when fired at a particular angle. The same equation that explained why the Earth bulges slightly at the equator also predicted the return of Halley's Comet decades before it actually appeared. For the first time in human history, someone had demonstrated that a single mathematical relationship could unify phenomena across the entire known universe. But Newton's gravitational law was just one part of a much larger mathematical framework that he developed for understanding all motion and change in the natural world. His three laws of motion provided a complete mathematical foundation for analyzing any mechanical system, no matter how simple or complex. The first law established the concept of inertia. Objects at rest remain at rest, and objects in motion continue in straight-line motion at constant velocity unless acted upon by an external force. This wasn't just an abstract principle. It was a precise mathematical statement that allowed exact predictions about how objects would behave in the absence of forces. Newton's second law, F equals EMA, provided the mathematical key for understanding how forces produce changes in motion. This deceptively simple equation contained within it the power to analyze everything from the collision of billiard balls to the precession of planetary orbits. By specifying the exact mathematical relationship between force, mass, and acceleration, Newton had created a tool that could, in principle, predict the future motion of any mechanical system once its current state and the forces acting on it were known. The third law, for every action there is an equal and opposite reaction, revealed a deep symmetry in nature that ensured the conservation of momentum in all physical interactions. This wasn't just another useful rule. It was a fundamental constraint that limited how forces could operate in the universe. The fact that all forces come in equal and opposite pairs meant that the total momentum of an isolated system could never change, regardless of how complex the internal interactions might become. Together, these three laws created what contemporaries called the Newtonian world machine, a vision of the universe as a vast, mechanical system where every motion and interaction could be calculated with mathematical precision. Given complete knowledge of the positions and velocities of all particles in the universe at any moment, along with the forces acting between them, Newton's laws made it theoretically possible to calculate the entire future and past history of the cosmos with perfect accuracy. This mechanical worldview reached its most extreme expression in the writings of Pierre-Simon Laplace, who articulated what came to be known as Laplace's demon, an imaginary intelligence that knew the precise location and momentum of every atom in the universe and could use Newton's laws to predict all future states and retrodict all past states. According to Laplace, Nothing would be uncertain, and the future, as the past, would be present to its eyes. The universe was like a gigantic clockwork mechanism, wound up at the moment of creation, and thereafter running according to mathematically precise laws that left no room for genuine chance or uncertainty. The success of Newtonian mechanics in predicting and explaining natural phenomena was so spectacular that it seemed to confirm the most optimistic hopes of the scientific revolution. Mathematics really was the language of nature, and human reason really was capable of unlocking the deepest secrets of the cosmos. Newton's Principia Mathematica, published in 1687, demonstrated that three simple mathematical laws could explain the motion of everything, from planets to projectiles, from comets to cannonballs, from pendulums to planetary moons. But perhaps even more important than Newton's specific discoveries was the methodological framework he established for discovering physical laws. Newton showed that the path to understanding nature required several key elements: careful empirical observation to establish the facts that needed explanation, mathematical analysis to identify the quantitative relationships between different variables, theoretical reasoning to propose general principles that could account for these relationships, and rigorous testing to verify that these principles could make accurate predictions about previously unobserved phenomena. This Newtonian methodology became the template for all subsequent scientific inquiry. Physical laws weren't just philosophical speculations or mathematical curiosities. They were precise, quantitative descriptions of natural regularities that had been verified through careful observation and experimentation. They possessed predictive power, allowing scientists to calculate future events with mathematical precision. They displayed universality, applying the same way in all locations and at all times. And they exhibited explanatory power, showing how apparently diverse phenomena could be understood as manifestations of a small number of fundamental principles. The discovery of physical laws also revealed something profound about the relationship between human consciousness and cosmic structure. The fact that mathematical relationships discovered through pure reasoning could describe natural phenomena with such precision suggested that the human mind and the universe were somehow perfectly matched to each other. Either the universe was intrinsically mathematical, or human beings had evolved specifically to understand mathematical relationships, or both. This opened up deep philosophical questions about the nature of mathematical truth and its relationship to physical reality that continue to puzzle scientists and philosophers today. Newton's work also established the concept of the conservation laws that would become central to all subsequent physics. The conservation of momentum, which followed directly from his third law, showed that certain quantities remained constant even as everything else in a system changed. The conservation of energy, though not fully understood until the 19th century, was implicit in Newton's analysis of mechanical systems. These conservation laws represented the deepest expression of consistency in natural law. They identified quantities that literally could not change, no matter what forces were acting or what interactions were taking place. The birth of physical laws in the 17th century marked a turning point in human understanding of cosmic consistency. Where the ancient Greeks had intuited that the universe might be rationally ordered, Newton and his contemporaries proved it through mathematical demonstration. They showed that the same quantitative relationships govern natural phenomena across all scales of space and time, from the smallest mechanical interactions to the largest cosmic motions. This wasn't just a useful human way of organizing observations about nature. It revealed something fundamental about the structure of reality itself. The Newtonian synthesis established once and for all that the universe follows consistent rules, that these rules can be expressed in mathematical language, and that human beings possess the intellectual capacity to discover and understand these rules through careful observation and mathematical analysis. This achievement laid the foundation for everything that followed in the development of modern science. From Maxwell's equations for electromagnetism to Einstein's theories of relativity to the quantum mechanical description of atomic and subatomic phenomena. The birth of physical laws in the 17th century represented humanity's first glimpse of the mathematical architecture underlying all of cosmic reality. The spectacular success of Newton's mathematical laws in describing and predicting natural phenomena created a puzzle that has haunted scientists and philosophers for centuries. Why does mathematics work so unreasonably well in describing the physical universe? This isn't a trivial question or mere philosophical curiosity. When we step back and think about it objectively, the effectiveness of mathematics and physics is genuinely mysterious, perhaps even miraculous. Human beings evolved to survive on the African savanna, hunting animals and gathering plants, navigating social relationships and avoiding predators. There's no obvious evolutionary reason why brains shaped by these primitive survival needs should be capable of understanding quantum mechanics, general relativity, or the mathematical structure of black holes. Yet somehow, mathematical concepts develop through pure abstract reasoning, often with no thought of practical application, turn out to describe the deepest workings of physical reality with stunning precision. This mystery was articulated most eloquently by the physicist Eugene Wigner in his famous 1960 essay, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner was struck by the fact that mathematical theories developed by mathematicians for their own aesthetic and logical reasons, with no regard for physical applications, repeatedly turned out to provide exact descriptions of natural phenomena. He wrote, "The mathematical formulation of the physicist's often crude experience leads in an uncanny number of cases to an amazingly accurate description of a large class of phenomena. This wasn't just a matter of mathematics being a useful tool for organizing observations or making rough approximations. Mathematics was providing exact, precise descriptions of natural behavior that were often more accurate than direct empirical measurements." Consider the extraordinary example of James Clerk Maxwell's equations for electromagnetism, developed in the 1860s. Maxwell wasn't trying to invent new technology or solve practical engineering problems. He was attempting to create a mathematically elegant unification of electricity and magnetism, two phenomena that had previously been studied as completely separate domains. Working purely from mathematical considerations about how electric and magnetic fields should relate to each other, Maxwell derived a set of four equations that completely described all electromagnetic phenomena. But when he analyzed these equations mathematically, he discovered something completely unexpected. They predicted the existence of electromagnetic waves that traveled through space at a specific speed, which turned out to be exactly the speed of light. This mathematical prediction was so precise and unexpected that Maxwell initially doubted it himself. His equations were telling him that light was nothing more than oscillating electromagnetic fields, and that there should exist other electromagnetic waves at different frequencies that were invisible to human eyes. This was pure mathematical reasoning, leading to a physical discovery that had never been observed or even imagined. Within a few decades, Heinrich Hertz had experimentally confirmed the existence of radio waves, and the entire electromagnetic spectrum, from gamma rays to radio waves, had been discovered, all predicted in advance by Maxwell's mathematical equations. But Maxwell's triumph raises the deeper question: why should mathematical relationships derived from abstract reasoning describe physical phenomena at all? Maxwell didn't derive his equations from careful observations of electromagnetic waves, because electromagnetic waves hadn't been discovered yet. He derived them from mathematical principles of symmetry and consistency. And only afterward did experiment reveal that nature actually behaves according to these mathematical relationships. This suggests that mathematics isn't just a useful tool for describing nature after the fact. It's somehow more fundamental than empirical observation itself. Albert Einstein provided an even more dramatic example of mathematics anticipating physical reality. When Einstein developed his theory of general relativity, he wasn't responding to unexplained experimental observations or trying to solve practical problems. He was pursuing a purely theoretical goal: creating a mathematical theory that would be consistent with both special relativity and the principle that all reference frames are equivalent. Working from these abstract mathematical requirements, Einstein derived field equations that described gravity not as a force, but as the curvature of space-time itself. The mathematical consequences of Einstein's equations were so strange that Einstein himself initially rejected some of them. The equations predicted the existence of black holes, regions of space-time where gravity becomes so strong that not even light can escape. Einstein thought this was a mathematical artifact that couldn't exist in physical reality. The equations predicted gravitational waves, ripples in space-time itself that would propagate at the speed of light. Einstein doubted whether these waves could actually be detected. The equations predicted that massive objects would cause time to run slower and space to contract. Einstein worried that these effects might be too small to measure. But in every case, subsequent observations confirmed exactly what the mathematics predicted. Black holes were discovered and are now routinely observed by astronomers. Gravitational waves were detected by LIGO detectors in 2015, exactly as Einstein's equations predicted. Time dilation and length contraction have been measured with extraordinary precision and are essential for the operation of GPS satellites. The mathematics knew better than Einstein himself what physical reality was like. Perhaps even more remarkably, Einstein's equations predicted that the universe itself must be either expanding or contracting. It cannot be static. When Einstein first derived this result mathematically, the idea of an expanding universe seemed so absurd that he added an arbitrary cosmological constant to his equations to force them to predict a static universe. But within a few years, Edwin Hubble's observations showed that the universe really is expanding, exactly as Einstein's original equations had predicted. Einstein later called the cosmological constant the greatest blunder of my life. But even his blunder turned out to be prescient, as modern observations suggest that a cosmological constant, now called dark energy, really does exist and is causing the expansion of the universe to accelerate. The pattern repeats throughout the history of physics. Mathematical theories developed for abstract reasons turn out to describe physical reality with uncanny precision. Paul Dirac's mathematical analysis of quantum mechanics predicted the existence of antimatter before anyone had observed it. Murray Gell-Mann's mathematical classification of subatomic particles predicted the existence of quarks before experimental evidence confirmed their reality. Peter Higgs's mathematical analysis of symmetry breaking predicted the existence of the Higgs boson decades before it was detected at the Large Hadron Collider. This unreasonable effectiveness of mathematics becomes even more mysterious when we consider that mathematics itself seems to be a purely human construction. Mathematical objects like numbers, geometric shapes, and algebraic relationships don't exist in the physical world in any obvious sense. You can find 3 apples or 5 rocks, but you'll never find the number 3 or the number 5 just sitting around in nature. You can observe circular objects like wheels or planetary orbits, but you'll never encounter a perfect mathematical circle with exactly 0 thickness and infinite precision. Mathematical relationships are abstract mental constructs that exist only in human consciousness and the symbolic systems we use to represent them. Yet these abstract human constructs turn out to describe the behavior of physical reality more accurately than any direct empirical observation. This suggests one of several deeply puzzling possibilities. Perhaps mathematical relationships aren't human inventions at all, but discoveries of objective features of reality that exist independently of human consciousness. According to this Platonist view, mathematical objects exist in some abstract realm, and both human minds and physical systems somehow access or embody these eternal mathematical truths. When mathematicians discover new mathematical theorems, they're not creating anything new. They're uncovering timeless relationships that were always there, waiting to be found. Alternatively, perhaps the universe literally is mathematics, and what we call physical reality is simply the playing out of mathematical relationships. According to this mathematical universe hypothesis, proposed by MIT cosmologist Max Tegmark, there's no distinction between mathematical and physical existence. Every mathematical structure that's logically consistent corresponds to a physical reality, and our universe is simply one particular mathematical structure among infinitely many others. From this perspective, the effectiveness of mathematics and physics isn't mysterious at all. It's inevitable, because physics just is mathematics. A third possibility is that the apparent effectiveness of mathematics is a selection effect. Perhaps consciousness can only evolve in universes that are mathematically structured, because only mathematically structured universes remain stable and predictable long enough for complex information processing systems to develop. We observe mathematical relationships in nature not because all of reality is mathematical, but because non-mathematical realities don't produce observers capable of noticing their non-mathematical character. This anthropic explanation suggests that the universe appears mathematical to us because we couldn't exist in a non-mathematical universe. Yet another possibility is that human mathematical intuition evolved specifically to understand the mathematical structure of physical reality. Perhaps the same evolutionary processes that shaped our capacity for pattern recognition, spatial reasoning, and causal inference also gave us insight into the mathematical relationships that govern natural phenomena. Our brains evolved in a universe that really is mathematically structured, so it's not surprising that mathematical thinking turns out to be effective for understanding natural phenomena. The mystery isn't that mathematics works in physics, it's that we're smart enough to discover and understand the mathematical relationships that were always there. But this evolutionary explanation faces its own puzzles. The mathematical concepts that prove most effective in fundamental physics, complex numbers, infinite dimensional Hilbert spaces, non-commutative algebras, differential geometry on curved manifolds, seem far removed from anything our ancestors would have encountered in their prehistoric environment. How could natural selection have prepared us to understand mathematical structures that have no obvious connection to hunting, gathering, mating, or avoiding predators? The mathematical sophistication required to understand quantum field theory, or general relativity, seems to far exceed anything that survival on the African savanna would have required. The mystery deepens when we consider that the most fundamental physical theories often involve mathematical concepts that violate our evolved intuitions about how reality should behave. Quantum mechanics requires us to think about particles that exist in multiple places simultaneously and become entangled across arbitrary distances. General relativity requires us to understand spacetime as a curved manifold where parallel lines can intersect and straight paths through space can be curved paths through spacetime. These concepts are not only unintuitive, they're actively counterintuitive, contradicting the common sense understanding of reality that our evolved psychology provides. Yet somehow, human mathematicians and physicists have managed to develop mathematical frameworks that capture these counterintuitive aspects of reality with extraordinary precision. This suggests that our mathematical capabilities extend far beyond what evolutionary pressures could have directly selected for. Perhaps mathematical reasoning provides access to aspects of reality that transcend the particular evolutionary history of human consciousness. Mathematics might be a kind of cognitive telescope that allows us to see far beyond the limited domain of experience that shaped our ancestors' mental capacities. The effectiveness of mathematics in physics also raises questions about the relationship between mathematical truth and physical truth. When mathematicians prove theorems about abstract mathematical objects, are they discovering truths about the structure of physical reality? When physicists use mathematics to describe natural phenomena, are they uncovering the mathematical essence of nature? Or are they imposing mathematical structure onto fundamentally non-mathematical processes? The fact that mathematical predictions so often turn out to be physically correct suggests that mathematical and physical truth are intimately connected, but the nature of this connection remains mysterious. Perhaps the deepest puzzle is that mathematics often reveals aspects of physical reality that are completely inaccessible to direct empirical observation. Maxwell's equations revealed the existence of the entire electromagnetic spectrum. Einstein's equations revealed the curvature of spacetime and the existence of gravitational waves. Schrödinger's equation revealed the wave-like nature of matter and the probabilistic structure of quantum reality. Dirac's equation revealed the existence of antimatter. In each case, pure mathematical reasoning led to discoveries about physical reality that no amount of ordinary empirical observation could have revealed. This suggests that mathematics provides a kind of enhanced perception that allows human consciousness to detect aspects of reality that are invisible to ordinary sensory experience. Mathematical reasoning seems to be a method for seeing beyond the surface appearances of natural phenomena to discover the deeper structural relationships that govern how things really behave. But why should abstract symbolic manipulations in human consciousness provide access to objective features of physical reality? Why should the internal logical relationships between mathematical concepts correspond to the external causal relationships between physical events? The unreasonable effectiveness of mathematics in the natural sciences remains one of the deepest and most puzzling aspects of our scientific understanding of the universe. It suggests that there's something fundamental about the relationship between consciousness, mathematics, and physical reality that we don't yet understand. Perhaps consciousness, mathematics, and physics are all different aspects of some more fundamental reality that transcends the usual distinctions between mind and matter, between abstract reasoning and empirical observation, between human thought and cosmic structure. The fact that mathematics works so well in describing the universe might be our first clue to understanding this deeper unity. To understand why the universe follows consistent rules, we need to delve into one of the most profound and beautiful concepts in all of physics: symmetry. But we're not talking about the simple symmetries you might observe in a butterfly's wings or a snowflake's crystalline structure. Though these provide important clues, we're talking about abstract mathematical symmetries that form the invisible architecture underlying all of physical reality. Symmetries so fundamental that they literally create the conservation laws and consistent rules that govern everything from subatomic particles to galactic superclusters. These symmetries are hidden from direct observation, yet they determine every physical process that has ever occurred or ever will occur in the universe. The concept of symmetry in physics is both more abstract and more powerful than symmetry in everyday experience. When physicists talk about symmetry, they're referring to transformations that leave something unchanged. A sphere has rotational symmetry because it looks exactly the same no matter how you rotate it. A mathematical equation has symmetry if it remains valid under certain transformations of its variables. The physical laws of the universe have symmetries if they continue to work the same way under various changes in our perspective or coordinate system. But here's the crucial insight that revolutionized our understanding of natural law. These abstract mathematical symmetries aren't just convenient mathematical tools or aesthetic curiosities. They're the fundamental principles from which all physical laws emerge. This profound connection between symmetry and physical law was discovered in 1915 by Emmy Noether, a German mathematician whose theorem ranks among the most important results in the history of science. Though it remains largely unknown outside of professional physics and mathematics, Noether's theorem establishes a precise mathematical relationship between symmetries and conservation laws, showing that every continuous symmetry of a physical system corresponds to a quantity that must be conserved throughout all physical processes. This isn't just a useful observation or an interesting mathematical coincidence. It's a fundamental principle that explains why the universe follows consistent rules at the deepest possible level. Consider the symmetry of time translation, the fact that the laws of physics work the same way today as they did yesterday, and the same way they'll work tomorrow as they do today. This seems obvious, almost trivial, but Noether's theorem reveals that this temporal symmetry automatically generates the law of energy conservation. Because the fundamental equations of physics don't change from moment to moment, energy cannot be created or destroyed in any physical process. The total energy of an isolated system must remain constant, not because of some additional law imposed on top of the basic equations of motion, but as an inevitable, mathematical consequence of the fact that time translation leaves the laws of physics unchanged. Similarly, the symmetry of spatial translation, the fact that physics works the same way here as it does on the other side of the galaxy, automatically generates the law of momentum conservation. Because the fundamental equations don't depend on your absolute position in space, the total momentum of an isolated system cannot change. When a rocket fires its engines and accelerates forward, it must eject exhaust backward with exactly the right momentum to ensure that the total momentum of the rocket plus exhaust system remains constant. This isn't an additional constraint that we have to impose on rocket design. It's an inevitable consequence of the spatial symmetry of physical law. The symmetry of rotational invariance, the fact that physics works the same way regardless of which direction you're facing, generates the conservation of angular momentum. A figure skater spinning on ice demonstrates this conservation law when she pulls her arms close to her body and spins faster. But the deeper principle is that angular momentum conservation emerges automatically from the rotational symmetry of space itself. The universe has no preferred direction, no absolute up or down. And this directional democracy at the level of fundamental law creates the conservation principle that governs everything from spinning electrons to rotating galaxies. But Noether's theorem extends far beyond these familiar conservation laws to encompass much more abstract and subtle symmetries that govern the deepest levels of physical reality. The electromagnetic force, for example, emerges from what's called gauge symmetry, an abstract mathematical symmetry that's completely invisible to direct observation, but absolutely fundamental to how electric and magnetic fields behave. This gauge symmetry means that the physics of electromagnetism remains unchanged even if we apply certain mathematical transformations to the electromagnetic field at every point in space and time. The requirement that physics be gauge symmetric automatically generates Maxwell's equations for electromagnetism, along with the conservation of electric charge and all the other properties that make electromagnetic phenomena behave consistently throughout the universe. The weak nuclear force, responsible for certain types of radioactive decay, emerges from a different gauge symmetry that was initially hidden but becomes apparent when we understand how particles acquire mass through their interactions with the Higgs field. The strong nuclear force that binds quarks together inside protons and neutrons emerges from yet another gauge symmetry, one that involves abstract mathematical objects called color charges that have nothing to do with ordinary visual colors but determine how quarks interact through the exchange of gluons. Each of these fundamental forces exists because of a different symmetry principle and the specific properties of each force, their relative strengths, their ranges, the particles they affect, all emerge automatically from the mathematical structure of the underlying symmetry. The standard model of particle physics, our most complete and accurate description of fundamental reality, is essentially a catalog of the symmetries that govern the behavior of matter and energy at the smallest scales. Every particle in the standard model is defined by how it transforms under various symmetry operations. Electrons, muons, and tau particles form a family because they all have the same relationship to the symmetries of the weak force. Quarks come in 6 varieties, Because there are 6 different ways to satisfy the symmetry requirements of both the weak and strong forces. Neutrinos exist because the symmetries that generate the weak force require the existence of particles with exactly their properties. But perhaps even more remarkably, the Standard Model reveals that many of the symmetries that appear to govern fundamental physics are actually broken symmetries. Symmetries that were perfect in the early universe, but became imperfect as the universe cooled and evolved. The electromagnetic and weak forces were originally unified into a single electroweak force, but this symmetry was spontaneously broken when the universe cooled below a critical temperature, and the Higgs field acquired a non-zero value throughout space. This symmetry breaking is what gives most particles their mass and creates the distinction between photons, which remain massless, and the W and Z bosons of the weak force, which are extremely massive. The concept of spontaneous symmetry breaking helps explain one of the deepest mysteries about our universe. Why does matter exist at all, rather than being completely annihilated by antimatter? In the earliest moments after the Big Bang, the universe should have contained exactly equal amounts of matter and antimatter, and these should have completely annihilated each other, leaving nothing behind but photons. The fact that we exist at all means that some process must have created a tiny asymmetry between matter and antimatter, and this asymmetry appears to have emerged from the spontaneous breaking of a symmetry called CP symmetry, the combined symmetry of charge conjugation and parity inversion. The breaking of CP symmetry allowed slightly more matter than antimatter to survive the early universe's annihilation processes, providing the raw material from which all subsequent cosmic structure would emerge. Stars, planets, and living beings exist because of a broken symmetry that created a minute imbalance between matter and antimatter in the first moments after the Big Bang. Our entire material existence traces back to this single symmetry-breaking event that occurred when the universe was less than a second old. Symmetries also provide the foundation for our understanding of phase, transitions, the processes by which matter changes from one state to another as conditions change. When water freezes into ice, it undergoes a phase transition that breaks the rotational symmetry of the liquid state and creates the more ordered, crystalline structure of the solid state. Similarly, when the early universe cooled below critical temperatures, it underwent phase transitions that broke various symmetries and gave rise to the different forces and particle types we observe today. The entire history of cosmic evolution can be understood as a series of symmetry-breaking phase transitions, each one creating new types of order and complexity. But symmetries in physics go even deeper than explaining individual forces and conservation laws. They provide the conceptual framework for understanding why the universe exhibits mathematical structure at all. The fact that space and time have symmetries means that there are mathematical relationships that remain invariant under transformations, and these invariant relationships become the equations of physics. The consistency of natural law doesn't require some external cosmic legislator imposing rules on an otherwise chaotic universe. Consistency emerges automatically from the symmetry properties of the arena, space, and time, in which all physical processes take place. This leads to a profound insight about the relationship between mathematics and physics. Mathematics isn't just a useful tool that humans have developed to describe natural phenomena. Mathematics is the natural language for expressing symmetry relationships, and symmetry relationships are the fundamental structure of physical reality. When we write down mathematical equations to describe natural processes, we're not imposing artificial mathematical structure onto a fundamentally non-mathematical world. We're discovering the mathematical relationships that emerge inevitably from the symmetry properties of space, time, matter, and energy. The power of symmetry thinking in physics becomes apparent when we consider how it guides the search for new physical theories. When physicists try to extend the standard model to include gravity or to unify all the forces into a single theoretical framework, they don't start by making random guesses about possible equations. They start by asking what symmetries a more complete theory should possess, and then derive the equations that must follow from those symmetry requirements. String theory, for example, is built around the idea that fundamental particles are actually vibrations of tiny strings, and the different symmetries of these vibrations correspond to different particles and forces. The search for a theory of quantum gravity focuses on finding the right symmetry principles to unify general relativity's description of space-time curvature with quantum mechanics' description of matter and energy. Loop quantum gravity explores the consequences of making space and time themselves subject to quantum mechanical uncertainties. Causal set theory investigates whether spacetime might have a discrete atomic structure that breaks the continuous symmetries of general relativity at the smallest scales. Each approach is guided by different assumptions about what symmetries are fundamental and which ones might be emergent or approximate. Symmetries also provide a window into understanding the deepest cosmological questions about the structure and evolution of the universe as a whole. The cosmological principle, the assumption that the universe looks roughly the same in all directions when viewed on sufficiently large scales, is essentially a statement about the symmetries of space. These cosmological symmetries determine the possible mathematical forms that cosmological models can take, constraining the ways in which the universe can expand, contract, or evolve over time. The recent discovery of dark energy, the mysterious component that makes up about 68% of the universe and is causing cosmic expansion to accelerate, may indicate that our understanding of cosmological symmetries is incomplete. Dark energy appears to have properties that remain constant even as space expands, suggesting a new type of symmetry that we don't yet fully understand. Understanding the symmetry properties of dark energy may be the key to understanding why cosmic expansion is accelerating and what the ultimate fate of the universe will be. Perhaps most remarkably, symmetries provide a bridge between the subjective world of human consciousness and the objective structure of physical reality. The mathematical relationships that our minds discover through abstract reasoning turn out to correspond to actual symmetries in the structure of space, time, matter, and energy. This suggests that there's a deep connection between the logical structure of mathematical thinking and the symmetry structure of physical reality. When we engage in mathematical reasoning, we're not just manipulating arbitrary symbols according to conventional rules. We're exploring the same abstract relationships that determine how the universe actually behaves. The hidden architecture of symmetries reveals why the universe follows consistent rules, because consistency itself emerges from symmetry. The conservation laws, the fundamental forces, the properties of particles, the structure of space-time. All of these features of reality are automatic consequences of the symmetries that characterize the mathematical structure of existence itself. The universe doesn't follow rules because some external authority has imposed those rules. The universe follows rules because the rules emerge inevitably from the symmetry properties of the stage on which all cosmic drama unfolds. Just when scientists thought they had figured out the fundamental rules governing the universe through Newton's clockwork mechanics and Maxwell's elegant electromagnetic theory, nature threw them a curveball so bewildering that it shattered every intuitive notion about reality, causation, and the very meaning of physical law. The discovery of quantum mechanics in the early 20th century revealed that, at the most fundamental level, the universe operates according to principles that seem to mock our classical understanding of consistency and determinism. Yet paradoxically, this apparently chaotic quantum realm follows its own set of mathematical rules with such precision that quantum mechanics has become the most accurately tested theory in the history of science. This creates a profound puzzle. How can a universe that is fundamentally probabilistic and seemingly chaotic at its deepest level still exhibit the remarkable consistency that allows for the existence of stable atoms, predictable chemical reactions, and the reliable physical processes that make life possible? The quantum revolution began with Max Planck's reluctant discovery in 1900 that energy comes in discrete packets, or quanta, rather than flowing continuously as classical physics predicted. Planck himself was disturbed by this finding and spent years trying to reconcile it with classical theory, but the evidence was undeniable. Energy wasn't like water flowing from a faucet. It was more like coins being dispensed from a machine, coming in specific denominations with nothing in between. This discovery opened a door to a realm of reality where the familiar rules of classical physics simply didn't apply, where the very concepts of definite position, momentum, and trajectory lost their meaning. Werner Heisenberg delivered the next shock with his uncertainty principle in 1927, which demonstrated that there are fundamental limits to how precisely we can know certain pairs of properties of quantum particles. You cannot simultaneously measure both the exact position and the exact momentum of an electron, not because our measuring instruments are imperfect, but because the electron literally doesn't have both exact position and exact momentum at the same time. This wasn't a practical limitation of measurement technology. It was a fundamental feature of reality itself. The universe, at its most basic level, is inherently fuzzy and indefinite in ways that classical physics never anticipated. Erwin Schrödinger developed the mathematical framework that describes this quantum fuzziness through his famous wave equation, which treats particles not as definite objects with specific locations and velocities, but as probability waves spread out across space and time. According to Schrödinger's equation, an electron in an atom doesn't orbit the nucleus like a tiny planet orbiting the sun. Instead, it exists as a cloud of probability, with different regions of the cloud representing different likelihoods of finding the electron in various locations if a measurement is performed. The particle has no definite position until the moment of measurement, when the probability wave somehow collapses into a specific location. This wave-particle duality extends to all quantum objects, creating situations that seem to violate basic logic. In the famous double-slit experiment, individual photons or electrons appear to pass through both slits simultaneously when no one is watching, creating interference patterns that can only result from waves interacting with themselves. But when detectors are placed at the slits to determine which path each particle takes, the interference pattern disappears, and the particles behave like classical particles passing through one slit or the other. The act of observation seems to fundamentally change the nature of reality itself. Even more disturbing to classical intuitions is the phenomenon of quantum entanglement, first highlighted by Einstein, Podolsky, and Rosen in their famous 1935 paper that was intended to demonstrate the incompleteness of quantum mechanics. When two particles become entangled, measuring the properties of one particle instantly affects the properties of its partner, regardless of how far apart they might be. Einstein called this spooky action at a distance and refused to believe it could be a fundamental feature of nature. He insisted that there must be hidden variables that predetermine the outcomes of measurements, preserving the classical notion of local realism, where objects have definite properties independent of observation and influences cannot travel faster than light. But John Stuart Bell proved in 1964 that Einstein was wrong. Bell's theorem demonstrated mathematically that any theory based on local hidden variables would make predictions that differed from quantum mechanics in measurable ways. Subsequent experiments, particularly those conducted by Alain Aspect in the 1980s and many others since then, have consistently confirmed quantum mechanics and ruled out local realism. The universe really does exhibit non-local correlations that seem to violate our intuitive understanding of space, time, and causation. Two particles can remain connected in ways that transcend the normal limitations of space and time, behaving as components of a single quantum system even when separated by vast distances. This quantum weirdness raises a fundamental question about the nature of physical law. If reality is inherently probabilistic and non-local at the most fundamental level, how can the universe exhibit the remarkable consistency and predictability that we observe at larger scales? How do fuzzy, probabilistic quantum processes give rise to the precise, deterministic behavior of classical objects? The answer lies in the mathematical structure of quantum mechanics itself, which maintains its own form of consistency, even in the midst of fundamental uncertainty. The key insight is that while individual quantum measurements are genuinely random and unpredictable, the probabilities themselves are determined by precise mathematical laws. Schrödinger's equation tells us exactly how probability waves evolve over time, and these probability waves obey strict conservation laws and symmetry principles. The uncertainty isn't arbitrary chaos. It's governed by mathematical relationships that are just as rigid and precise as the equations of classical physics. Quantum mechanics doesn't abandon consistency. It relocates consistency from the level of individual events to the level of statistical patterns and probability distributions. This quantum consistency becomes apparent in the remarkable stability of atomic structure. According to classical physics, electrons orbiting atomic nuclei should continuously radiate electromagnetic energy and spiral into the nucleus within a fraction of a second, making stable atoms impossible. But quantum mechanics shows that electrons in atoms exist in discrete energy levels determined by the wave-like properties of matter. These quantum energy levels are mathematically precise and completely stable, explaining not only why atoms don't collapse, but also why the chemical elements have their specific properties and why the periodic table exhibits its regular patterns. The precision of quantum predictions is truly extraordinary. Quantum electrodynamics, the quantum theory of electromagnetic interactions, makes predictions about the magnetic properties of electrons that agree with experimental measurements to more than 10 decimal places. This represents the most accurate agreement between theory and experiment in the entire history of science. The apparent chaos of quantum mechanics gives rise to predictions that are more precise than any classical theory has ever achieved. But the transition from quantum uncertainty to classical determinism remains one of the deepest puzzles in physics. This is the measurement problem. How and when does a quantum system transition from existing in a superposition of multiple possible states to having definite, measurable properties? Schrödinger illustrated this puzzle with his famous thought experiment about a cat that remains simultaneously alive and dead until observed. But the puzzle extends to every quantum measurement and every classical phenomenon. One resolution to the measurement problem involves the concept of decoherence, first developed by Heinz-Dieter Zeh and Wojciech Zurek. According to decoherence theory, quantum systems naturally interact with their environments in ways that rapidly destroy quantum superpositions and create the appearance of classical behavior. When a quantum system becomes entangled with many particles in its environment, the delicate phase relationships that maintain quantum superpositions are scrambled beyond recovery. This environmental interaction doesn't solve the measurement problem completely, but it explains why quantum behavior is typically observed only in carefully isolated systems, while classical behavior emerges naturally in complex, noisy environments. The consistency of quantum mechanics also emerges through the mathematical structure of quantum field theory, which treats particles as excitations in underlying quantum fields that permeate all of space. In quantum field theory, what we call empty space is actually filled with quantum fields fluctuating according to the uncertainty principle. These vacuum fluctuations create virtual particles that pop into existence and disappear again within time intervals allowed by the uncertainty principle. While this might seem like pure chaos, these quantum fluctuations follow precise mathematical laws and produce measurable effects, such as the Casimir force between closely spaced metal plates and small corrections to the energy levels of atoms. Quantum field theory also reveals how the fundamental forces emerge from symmetries, just as Emmy Noether's theorem predicts, but in the quantum context, these symmetries take on new meaning. The electromagnetic force arises from a local gauge symmetry that requires the existence of photons as the force-carrying particles. The weak nuclear force emerges from a different gauge symmetry that predicts the existence of W and Z bosons. The strong force comes from yet another gauge symmetry that requires gluons to carry the force between quarks. Each force exists because quantum field theory demands that the underlying equations respect certain symmetry principles. But quantum mechanics also introduces fundamental limits to the consistency of physical law through the uncertainty principle and the no-cloning theorem. The uncertainty principle means that there are fundamental limits to how much information can be extracted from a quantum system. The no-cloning theorem proves that it's impossible to make perfect copies of arbitrary quantum states, which means that quantum information has properties that classical information lacks. These limitations suggest that the universe's consistency might itself be limited by quantum mechanical principles. The interpretation of quantum mechanics remains controversial, with different interpretations offering radically different pictures of what quantum consistency actually means. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, maintains that quantum mechanics is a complete description of reality and that asking about the properties of quantum systems independent of measurement is meaningless. The many worlds interpretation, proposed by Hugh Everett III, suggests that all possible measurement outcomes actually occur in parallel universes, preserving determinism at the cost of multiplying realities beyond measure. The de Broglie-Bohm pilot wave theory maintains that particles do have definite positions and velocities, but these are guided by a quantum wave function that ensures non-local correlations. Each interpretation offers a different understanding of how quantum mechanics maintains consistency. In the Copenhagen interpretation, consistency emerges from the mathematical structure of quantum theory itself, even though the physical meaning of this mathematics remains fundamentally mysterious. In the many worlds interpretation, consistency is preserved because all mathematically possible outcomes actually occur, making the apparent randomness of quantum mechanics an artifact of our limited perspective within a single branch of the universal wave function. In pilot wave theory, consistency is maintained through deterministic hidden variables, but at the cost of accepting non-local influences that seem to violate relativity. The relationship between quantum mechanics and consciousness adds another layer of mystery to quantum consistency. Some interpretations suggest that consciousness plays a fundamental role in quantum measurement, collapsing wave functions and determining which potential realities become actual. While most physicists reject this consciousness-based interpretation, the role of observation in quantum mechanics continues to raise deep questions about the relationship between mind and physical reality. If consciousness is required to collapse wave functions, then the consistency of physical law might depend on the existence of conscious observers. Quantum error correction provides perhaps the most remarkable example of how consistency can emerge from quantum chaos. Just as classical computers use error correction codes to protect information from random noise, quantum computers must use quantum error correction to protect delicate quantum states from environmental decoherence. But quantum error correction is far more sophisticated than its classical counterpart, using the strange properties of quantum entanglement to detect and correct errors without destroying the quantum information being protected. This suggests that nature itself might use quantum error correction to maintain the stability and consistency of physical processes at the quantum level. The development of quantum computing and quantum information theory has revealed that quantum mechanics doesn't just describe the microscopic world. It provides new resources for computation and communication that have no classical analog. Quantum computers can solve certain problems exponentially faster than classical computers by exploiting quantum superposition and entanglement. Quantum cryptography can provide absolutely secure communication by using the no-cloning theorem to detect eavesdropping. These applications demonstrate that quantum chaos actually represents a more sophisticated form of order than classical determinism. The story of quantum mechanics reveals that consistency in the universe is far more subtle and profound than classical physics imagined. The apparent chaos of quantum uncertainty masks deeper mathematical structures that maintain their own forms of consistency while enabling the emergence of classical determinism at larger scales. Quantum mechanics doesn't abandon the idea that the universe follows consistent rules. It shows us that these rules operate at a level of reality that transcends our classical intuitions about space, time, causation, and objectivity. The quantum realm follows rules that are as precise and unforgiving as any classical law. But these rules govern probabilities, correlations, and information in ways that classical physics never anticipated. In the end, quantum mechanics reveals that the universe's consistency is even more remarkable than we originally thought, because it maintains mathematical precision and predictive power even in the face of fundamental uncertainty and non-locality. When we expand our investigation of cosmic consistency from the quantum realm to the largest scales of space and time, we encounter perhaps the most remarkable demonstration of universal law in all of science. The same physical principles that govern the behavior of subatomic particles in laboratory experiments also determine the formation of the first atomic nuclei in the primordial universe, guide the nuclear fusion processes in stellar cores, and dictate the extreme physics of black holes where space-time itself becomes so warped that our usual concepts of space and time break down. This cosmic consistency spans not just enormous ranges of size and energy, but also vast stretches of time, from the first microseconds after the Big Bang to the far future when the universe will have expanded and cooled beyond the point where new stars can form. The fact that the same mathematical relationships apply across these mind-boggling scales and epochs represents perhaps the strongest evidence we have that the universe really does follow consistent universal laws. The story of cosmic consistency begins in the first moments after the Big Bang, when the universe was unimaginably hot and dense, filled with a soup of fundamental particles and radiation at temperatures of billions of degrees. Within the first few minutes of cosmic history, as the universe expanded and cooled, protons and neutrons began to stick together through the strong nuclear force to form the first atomic nuclei. This process, called Big Bang nucleosynthesis, provides one of the most remarkable demonstrations of cosmic consistency in all of science. The nuclear physics that operates in particle accelerators and nuclear reactors today is exactly the same nuclear physics that operated 13.8 billion years ago, when the universe was less than 20 minutes old. The predictions of Big Bang nucleosynthesis are incredibly precise. Based on our understanding of nuclear physics and the expansion rate of the early universe, we can calculate exactly what fraction of the universe's ordinary matter should have been converted into hydrogen, helium, lithium, and other light elements during those crucial first minutes. These calculations predict that about 75% of ordinary matter should be hydrogen, about 25% should be helium-4, with tiny traces of deuterium, helium-3, and lithium-7. When astronomers observe the composition of the oldest stars and gas clouds in the universe, they find exactly these ratios, confirming that the same nuclear physics we study in laboratories today was operating with perfect consistency in the primordial universe. This agreement between theory and observation is so precise that it provides one of the strongest confirmations we have that the fundamental constants of nature, the strengths of the various forces, the masses of the fundamental particles, the speed of light, have remained exactly constant throughout cosmic history. If any of these constants had been different in the early universe, Big Bang nucleosynthesis would have produced different ratios of elements, and we would observe different compositions in ancient astronomical objects. The fact that we observe exactly the predicted ratios means that the laws of physics have remained consistent across billions of years of cosmic evolution. But cosmic consistency extends far beyond the first few minutes after the Big Bang to encompass the entire process of cosmic structure formation. The tiny fluctuations in density that we observe in the cosmic microwave background radiation, the afterglow of the Big Bang that we can still detect today, grew under the influence of gravity over billions of years to become the galaxies, galaxy clusters, and vast cosmic web of filaments that characterize the large-scale structure of the universe today. This process of gravitational growth follows Einstein's equations of general relativity with extraordinary precision, creating patterns that match theoretical predictions across scales ranging from individual galaxies to the largest observable structures in the cosmos. The cosmic microwave background itself provides a snapshot of the universe when it was only 380,000 years old, just after it had cooled enough for the first atoms to form and for light to travel freely through space for the first time. The tiny temperature variations in this radiation, measured to be only about 100 millionths of a degree, encode information about the density fluctuations that would eventually grow into all the cosmic structure we see today. The fact that we can use our current understanding of physics to make detailed predictions about the statistical properties of these fluctuations, and that these predictions match observations with remarkable precision, demonstrates that the same physical laws governed the universe when it was 1,000 times smaller and billions of times denser than it is today. Stellar evolution provides another extraordinary demonstration of cosmic consistency across vast scales of time and space. Every star in the universe, from the smallest red dwarfs to the most massive blue giants, operates according to the same fundamental principles of nuclear physics, thermodynamics, and gravity. The nuclear fusion reactions that power stars follow exactly the same rules, whether they occur in our sun or in a star on the other side of the galaxy that formed billions of years ago from a completely different gas cloud. The hydrostatic equilibrium that balances gravitational collapse against radiation pressure operates the same way in every stellar core, creating the main sequence relationship that allows astronomers to determine stellar properties from their colors and brightnesses. The consistency of stellar physics allows us to use stars as standard candles and chronometers, measuring cosmic distances and ages based on our understanding of how different types of stars evolve over time. The fact that these methods give consistent results when applied to stars throughout the observable universe confirms that nuclear physics, thermodynamics, and gravity operate the same way everywhere in space and at all times in cosmic history. When we observe a type Ia supernova in a distant galaxy, we can be confident that it resulted from exactly the same physical process, the thermonuclear explosion of a white dwarf star that has accreted matter beyond the Chandrasekhar limit. That would occur if the same type of system existed in our own galactic neighborhood. The chemical evolution of the universe provides yet another demonstration of cosmic consistency. The heavy elements that make planets and life possible, carbon, oxygen, silicon, iron, and all the rest, were forged in the nuclear furnaces of stars and dispersed into space when those stars died in supernova explosions. This process of stellar nucleosynthesis follows exactly the same nuclear physics throughout the universe. which is why astronomers can observe distant galaxies and determine their chemical compositions based on the spectral lines produced by atoms that follow the same quantum mechanical rules as atoms in our own laboratories. The gradual enrichment of the universe with heavy elements over cosmic time creates a consistent pattern that we can observe in stars of different ages and locations. Older stars, formed when the universe was young and had not yet had time to produce many heavy elements, show lower abundances of elements heavier than helium. Younger stars, formed from gas that had been enriched by previous generations of stellar evolution, show higher heavy element abundances. This metallicity gradient, observed consistently throughout the universe, confirms that stellar nucleosynthesis has been operating according to the same physical laws for billions of years. Black holes represent perhaps the most extreme test of cosmic consistency, creating conditions so extreme that space-time itself becomes severely curved, and the usual concepts of space and time lose their familiar meanings. Yet even in these most exotic environments, the laws of physics maintain their consistency. Einstein's equations of general relativity, developed to describe the geometry of space-time under the influence of matter and energy, successfully predict every observed property of black holes, from their event horizons to their effects on nearby matter and light. The recent direct detection of gravitational waves from merging black holes by the LIGO and Virgo collaborations provides spectacular confirmation that Einstein's equations remain accurate even under the most extreme conditions imaginable. When two black holes spiral into each other and merge, they create ripples in space-time itself that propagate outward at the speed of light. The waveforms detected by gravitational wave observatories match the predictions of general relativity with extraordinary precision, confirming that the same equations that describe the gentle curvature of spacetime around Earth also accurately describe the violent warping of spacetime during black hole mergers. Stephen Hawking's discovery that black holes emit thermal radiation represents one of the most remarkable demonstrations of how different areas of physics maintain consistency with each other. Hawking radiation emerges from the application of quantum mechanical principles to the curved space-time geometry around black holes, showing that thermodynamics, quantum mechanics, and general relativity all fit together in a consistent theoretical framework. The temperature of this radiation is inversely proportional to the black hole's mass, meaning that more massive black holes are colder, while smaller black holes are hotter. This relationship, derived purely from theoretical considerations, has never been directly observed because the temperatures involved are far too small to measure for astrophysical black holes, but it represents a profound connection between gravity, quantum mechanics, and statistical physics. The holographic principle, which emerged from studies of black hole physics, suggests an even deeper form of cosmic consistency. This principle proposes that all the information contained within a region of space can be encoded on the boundary of that region, much like a hologram encodes three-dimensional information on a two-dimensional surface. If the holographic principle is correct, it would mean that the apparent three-dimensional nature of space might be an emergent property of more fundamental two-dimensional physics, providing a new perspective on why physical laws remain consistent across different scales and dimensions. Dark matter and dark energy, which together make up about 95% of the universe, present both challenges and confirmations of cosmic consistency. Dark matter, which outweighs ordinary matter by a factor of about 5 to 1, reveals itself only through its gravitational effects on visible matter and radiation. Yet these gravitational effects follow Einstein's equations exactly, allowing astronomers to map the distribution of dark matter throughout the universe using gravitational lensing and galaxy dynamics. The fact that dark matter behaves gravitationally, just like ordinary matter, despite having completely different particle physics properties, confirms that gravity operates consistently for all forms of matter and energy. Dark energy presents a more mysterious challenge to our understanding of cosmic consistency. This component, which makes up about 68% of the universe's energy density, appears to cause the expansion of the universe to accelerate rather than slow down as gravity would normally dictate. Yet even this mysterious dark energy appears to behave consistently throughout space and time, maintaining a constant energy density even as space expands. This consistency in dark energy's properties is itself puzzling, because most forms of energy become diluted as space expands. But it demonstrates that even phenomena we don't understand appear to follow consistent rules. The cosmic web, the largest scale structure in the universe consisting of galaxy filaments separated by vast voids, provides a final demonstration of cosmic consistency across the most enormous scales accessible to observation. Computer simulations of cosmic structure formation, based on our understanding of gravity, dark matter, and dark energy, successfully reproduce the statistical properties of the observed cosmic web in remarkable detail. The fact that the same physical laws can explain phenomena ranging from the formation of individual galaxies to the structure of the universe on scales of billions of light years confirms that cosmic consistency extends to the largest scales we can observe. Looking toward the future, cosmic consistency implies that we can make reliable predictions about the long-term evolution of the universe. Based on current observations of dark energy and the expansion rate, cosmologists predict that the universe will continue expanding and cooling for trillions of years, eventually reaching a state where star formation ceases and existing stars burn out one by one. Even in this far future, the fundamental laws of physics should remain the same, with protons eventually decaying, if current theories are correct, and black holes slowly evaporating through Hawking radiation until nothing remains but a dilute gas of elementary particles and photons. The story of cosmic consistency, from the Big Bang to black holes and beyond, reveals that the universe operates according to a remarkably small set of fundamental principles that remain constant across all scales of space and time. The same quantum mechanics that governs atomic interactions also determines the properties of stellar cores and the emission of Hawking radiation from black holes. The same general relativity that describes the curvature of space-time around massive objects also governs the expansion of the universe and the formation of cosmic structure. The same thermodynamics that operates in laboratory experiments also determines the nuclear fusion rates in stellar cores and the thermal properties of black holes. This cosmic consistency is not guaranteed by any logical principle. It is an empirical discovery about the actual structure of our universe that continues to amaze scientists and philosophers as our observations extend to ever more extreme environments and ever more remote epochs in cosmic history. The remarkable consistency of physical laws throughout our observable universe raises a profound and deeply unsettling question that strikes at the heart of everything we've discussed so far. What if our universe, with its precisely calibrated constants and elegantly consistent rules, is not unique? What if there exists an infinite collection of universes, each with its own set of physical laws, its own values for the fundamental constants, and its own particular version of cosmic consistency or inconsistency? This possibility, known as the multiverse hypothesis, fundamentally challenges our understanding of why the universe follows consistent rules by suggesting that consistency itself might be nothing more than a cosmic accident, a fortunate roll of the dice in an infinite casino where every possible combination of physical laws plays out somewhere in the vast ensemble of realities. The multiverse question emerges most directly from what physicists call the fine-tuning problem, one of the most perplexing puzzles in modern cosmology. When we examine the fundamental constants that govern physical reality, the strength of gravity, the electromagnetic force, the strong and weak nuclear forces, the mass of the proton, the charge of the electron, and dozens of other parameters, we find that they appear to be calibrated with extraordinary precision to allow for the existence of complex structures like stars, planets, atoms, molecules, and ultimately life itself. Change any of these constants by even tiny amounts, and the universe becomes a barren wasteland incapable of producing the rich complexity we observe. Consider the strength of the gravitational force, characterized by Newton's gravitational constant. If gravity were significantly stronger than it actually is, stars would burn through their nuclear fuel so rapidly that they would explode as supernovas before planets could form and life could evolve. If gravity were significantly weaker, gas clouds would never collapse densely enough to ignite nuclear fusion, and stars would never form at all. The actual strength of gravity appears to fall within a narrow range that allows both stellar formation and stellar longevity, creating the conditions necessary for planetary systems and biological evolution. The fine-tuning extends to the nuclear forces with even more dramatic precision. The strong nuclear force that binds protons and neutrons together in atomic nuclei must be calibrated within extremely tight tolerances to allow for the existence of the chemical elements that make complexity possible. If the strong force were slightly weaker, protons and neutrons couldn't stick together to form stable nuclei, and the universe would contain only hydrogen. If the strong force were slightly stronger, protons and neutrons would bind so tightly that hydrogen itself would be unstable, and nuclear fusion would occur so readily that all the hydrogen in the universe would have been converted to heavier elements almost immediately after the Big Bang. The electromagnetic force presents its own fine-tuning puzzles. This force determines the sizes of atoms, the energies of chemical bonds, and the stability of molecular structures. If electromagnetism were stronger, electrons would be bound so tightly to atomic nuclei that chemical reactions would be impossible, preventing the formation of molecules and biological systems. If electromagnetism were weaker, atoms would be so large and loosely bound that stable chemistry could not exist. The actual strength of the electromagnetic force falls within the narrow range that allows for both atomic stability and chemical complexity. Perhaps most remarkably, the cosmological constant, the parameter that determines the rate of cosmic expansion and is associated with the mysterious dark energy that dominates our universe, appears to be fine-tuned to a degree that seems almost impossible to believe. Theoretical calculations based on quantum field theory predict that the cosmological constant should be larger than its observed value by a factor of 10 to the 120th power, making this the worst prediction in the history of physics. Yet if the cosmological constant were anywhere near its theoretically predicted value, space would expand so rapidly that matter could never clump together to form galaxies, stars, or planets. The observed value is just small enough to allow cosmic structure formation while still being large enough to eventually dominate the universe's expansion. This fine-tuning problem presents us with three possible explanations, each with profound implications for our understanding of cosmic consistency. The first possibility is that the apparent fine-tuning is somehow necessary, that deeper physical principles we haven't discovered yet explain why the fundamental constants must have exactly the values they do. This would mean that our universe is the only possible universe, and the appearance of fine-tuning is an illusion created by our incomplete understanding of physics. If this is true, then the consistency of physical laws isn't accidental, but inevitable, emerging from logical principles that make any other set of laws impossible. The second possibility is that the fundamental constants were deliberately set by some intelligence or designer to allow for the existence of complex structures and life. This teleological explanation attributes the fine-tuning to purposeful design, suggesting that the universe's consistency serves some cosmic purpose. However, this explanation raises more questions than it answers and lies outside the domain of scientific investigation, making it impossible to test or verify through empirical observation. The third possibility, and the one that has gained the most attention from physicists and cosmologists, is that our universe is just one member of an enormous ensemble of universes with randomly distributed values for their fundamental constants. This multiverse scenario, most universes have constants that don't allow for complexity or life, but a tiny fraction happen to have the right values by pure chance. We find ourselves in one of these rare, habitable universes not because of design or necessity, but because only such universes can produce observers capable of wondering about fine-tuning in the first place. The multiverse hypothesis receives theoretical support from several different areas of modern physics. Cosmic inflation, the theory that explains why our observable universe is so uniform and flat, naturally leads to the prediction of eternal inflation and bubble universes. According to this scenario, inflation never actually ends globally, but continues eternally, creating an infinite number of bubble universes like our own. Each bubble universe begins with its own Big Bang and evolves according to its own set of physical laws, with the fundamental constants determined by the particular way that various quantum fields settled into their ground states as that universe cooled. String theory, our most ambitious attempt at a theory of quantum gravity and unification of all forces, provides another route to the multiverse. String theory suggests that the fundamental constants of physics are determined by the geometric shape of extra-spatial dimensions beyond the three we experience directly. There are an enormous number of possible shapes for these extra dimensions. Recent calculations suggest about 10 to the power of 500 different possibilities, each corresponding to a different set of physical laws and fundamental constants. If all of these possibilities are realized somewhere in a vast multiverse, then our particular set of physical laws becomes just one option among an unimaginably large number of alternatives. Quantum mechanics itself might generate multiple universes through the many worlds interpretation proposed by Hugh Everett III. According to this interpretation, every quantum measurement doesn't just produce one outcome, but actually produces all possible outcomes, with each outcome occurring in a separate branch of the universal wave function. If this is correct, then every quantum event throughout the history of the universe has been splitting reality into multiple parallel branches, creating a vast multiverse of quantum possibilities. While these parallel universes would all start with the same physical laws, their different quantum histories could lead to dramatically different outcomes, and perhaps even different effective laws of physics at macroscopic scales. The anthropic principle provides the logical framework for understanding how the multiverse might explain fine-tuning. The weak anthropic principle simply observes that we necessarily find ourselves in a universe compatible with our existence, since we couldn't exist in universes with incompatible physical laws. This is a tautology, but becomes meaningful in the context of a multiverse. If most universes in the multiverse are sterile and lifeless, then the fact that we observe a life-friendly universe tells us nothing about design or necessity. It's simply a selection effect. The strong anthropic principle goes further, suggesting that the universe must have properties that allow observers to develop within it at some stage. This principle is more controversial because it seems to imply that the existence of observers is somehow necessary or fundamental to the nature of reality itself. In the context of the multiverse, the strong anthropic principle would suggest that observer-friendly universes are not just rare accidents, but somehow privileged or more fundamental than sterile universes. However, the multiverse hypothesis faces serious theoretical and philosophical challenges. The most fundamental problem is that if the multiverse contains every possible universe, then it becomes impossible to make any meaningful predictions about what we should observe. In an infinite ensemble of universes with every possible set of laws, every possible observation becomes equally likely, and the concept of scientific prediction loses all meaning. This leads to the measure problem. How do we calculate probabilities or make meaningful statements about what we should expect to observe in a truly infinite multiverse? The multiverse hypothesis also raises the problem of Boltzmann brains, random fluctuations that spontaneously create conscious observers without the complex evolutionary history that led to human consciousness. If the multiverse is infinite and contains every possible configuration of matter and energy, then it should contain far more Boltzmann brains than evolved observers like ourselves. This would mean that we should expect to be Boltzmann brains rather than evolved creatures, leading to a paradox that undermines our ability to trust our observations and reasoning about the multiverse itself. Another challenge comes from the difficulty of testing multiverse theories empirically. By definition, other universes in the multiverse are causally disconnected from our own, making direct observation impossible. While some theorists have proposed indirect ways to test multiverse theories, looking for collisions between bubble universes in the cosmic microwave background, or searching for signatures of extra dimensions. These tests remain speculative and may ultimately be impossible to perform. The multiverse hypothesis also raises profound questions about the nature of scientific explanation. Traditional science seeks to explain observed phenomena by identifying underlying laws and principles that make those phenomena necessary or at least highly probable. But if the multiverse is real, then the particular laws we observe might have no deeper explanation than random chance combined with anthropic selection. This would represent a fundamental shift in the nature of scientific understanding, replacing explanation with description and necessity with contingency. Some physicists argue that the multiverse hypothesis represents a retreat from the traditional goals of science rather than an advance in our understanding. Rather than seeking to understand why the universe has the particular laws it does, the multiverse hypothesis simply postulates that all possible laws exist somewhere, making the question of why our laws are special meaningless. This approach abandons the search for deeper principles in favor of an explanation that, while perhaps correct, provides no genuine understanding of why reality has the structure it does. The multiverse question also has implications for the meaning and value of scientific knowledge itself. If our universe is just one random sample from an infinite ensemble of possibilities, then the laws of physics we discover may have no broader significance beyond their local applicability to our particular cosmic neighborhood. The elegant mathematical relationships that govern our universe, the symmetries, conservation laws, and fundamental equations that we've discussed throughout this exploration might be nothing more than arbitrary accidents with no deeper meaning or purpose. Yet even if the multiverse hypothesis is correct, it doesn't eliminate the mystery of cosmic consistency within our own universe. The fact remains that our particular universe does follow consistent mathematical laws across all scales of space and time, from quantum mechanics to general relativity to cosmology. The multiverse hypothesis might explain why we find ourselves in a universe with consistent laws, but it doesn't explain how those consistent laws operate or why mathematical relationships provide such accurate descriptions of physical phenomena within our cosmic domain. The multiverse question ultimately forces us to confront the deepest philosophical questions about the nature of existence, explanation, and scientific understanding. If multiple universes with different physical laws really do exist, then the consistency of rules in our universe becomes a selection effect rather than a fundamental feature of reality. But if our universe is unique, then the consistency of its laws points toward deeper principles that we have yet to understand. Either way, the question of why the universe follows consistent rules remains as profound and mysterious as ever, whether the answer lies in the inevitable consequences of mathematical logic, the purposeful design of cosmic intelligence, or the anthropic selection effects operating across an infinite multiverse of possibilities. Even as we marvel at the extraordinary consistency of physical laws across the vast scales of space and time, we must confront a humbling reality. There are places in the universe where our most cherished and well-tested theories simply break down, where the elegant mathematical frameworks that describe everything from quantum particles to galactic clusters give us nonsensical answers, infinite values, or complete silence. These breakdowns are not mere technical inconveniences or signs of mathematical sloppiness. They represent fundamental limits to our current understanding of reality and point toward deeper mysteries that may require entirely new conceptual frameworks to resolve. The existence of these limits doesn't invalidate the remarkable consistency we observe throughout most of the universe, but it does remind us that our current picture of cosmic law is incomplete and that there may be aspects of reality that lie forever beyond human comprehension. The most dramatic breakdown of physical law occurs at the singularities that general relativity predicts lie at the centers of black holes, and at the moment of the Big Bang itself. When we apply Einstein's field equations to describe what happens as matter collapses under its own gravity, we find that the curvature of spacetime becomes infinite at certain points, creating what mathematicians call singularities. At these singularities, the fundamental quantities that characterize spacetime, its curvature, the density of matter and energy, the strength of gravitational fields, all become mathematically infinite. But infinity is not a physical quantity. It's a mathematical abstraction that signals the complete breakdown of our theoretical framework. At the singularity predicted to exist at the center of every black hole, our equations tell us that the curvature of spacetime becomes infinite while the volume of space shrinks to zero. This creates a situation where the normal concepts of space and time lose all meaning. We cannot describe what happens at the singularity. We cannot predict what emerges from it, and we cannot even meaningfully ask what exists there, since the very notion of location breaks down when space itself becomes infinitely curved. The singularity represents a boundary beyond which our current understanding of physics simply cannot penetrate. The Big Bang singularity presents an even more fundamental challenge to our understanding of cosmic consistency. According to our best current theories, all of space, time, matter, and energy emerge from an initial singularity of infinite density and temperature. But this description is clearly inadequate because it requires us to believe that something with infinite properties somehow gave rise to a universe with finite, measurable characteristics. The laws of physics themselves presumably emerge from this initial singularity. But how can we understand the origin of physical law using physical law itself? We face a logical circle that current physics cannot resolve. These singularities point toward the most profound limitation of our current understanding: the incompatibility between general relativity and quantum mechanics. General relativity treats spacetime as a smooth, continuous fabric that can be curved and distorted by matter and energy. Quantum mechanics treats space and time as fixed backgrounds against which quantum fields fluctuate according to the uncertainty principle. These two frameworks have been extraordinarily successful within their respective domains, but they give contradictory predictions when applied to situations where both quantum effects and gravitational effects become important, such as the interior of black holes or the first moments after the Big Bang. The Planck scale, where quantum gravitational effects become significant, represents a fundamental barrier to our current understanding of space and time themselves. At distances of about 10 to the negative 35th meters and time intervals of about 10 to the negative 43rd seconds, the uncertainty principle ensures that quantum fluctuations in the gravitational field become so large that the very notion of a definite space-time geometry breaks down. Space and time themselves become quantum mechanical, fluctuating between different possible geometries in ways that we cannot currently describe mathematically. This quantum foam represents a realm where our classical notions of space, time, causation, and physical law simply do not apply. The search for a theory of quantum gravity represents one of the greatest challenges in modern physics, but it also reveals fundamental limits to our ability to understand the deepest levels of reality. String theory, loop quantum gravity, causal set theory, and other approaches to quantum gravity all require mathematical frameworks so abstract and complex that they may forever remain beyond direct experimental verification. These theories operate at energy scales that are many orders of magnitude beyond what any conceivable particle accelerator could achieve, and they make predictions about aspects of reality that may be fundamentally unobservable. Even in domains where our current theories work well, we encounter limits that suggest the breakdown of reductionist thinking itself. Chaos theory demonstrates that even perfectly deterministic systems can exhibit behavior that is impossible to predict over long time periods. A double pendulum follows Newton's laws exactly, but its motion quickly becomes so sensitive to initial conditions that tiny uncertainties in measurement grow exponentially until long-term prediction becomes impossible. Weather systems, population dynamics, and many other natural phenomena exhibit this same chaotic behavior, showing that deterministic laws do not necessarily lead to predictable outcomes. The phenomenon of emergence presents another challenge to our understanding of how consistent rules relate to complex behavior. Consciousness emerges from the activity of neurons, but we have no clear understanding of how subjective experience arises from objective physical processes. Life emerges from chemistry, but the transition from non-living to living systems remains mysterious despite our detailed knowledge of biochemistry. Intelligence emerges from neural networks, but we cannot explain how information processing gives rise to understanding and meaning. These emergent phenomena suggest that there may be levels of reality that cannot be reduced to more fundamental physical laws, even when those laws operate with perfect consistency. The measurement problem in quantum mechanics represents perhaps the most fundamental limit to our understanding of physical law itself. Quantum mechanics provides extraordinarily accurate predictions about the statistical behavior of quantum systems, but it cannot tell us when or how a quantum superposition collapses into a definite measurement outcome. The theory describes probability waves with mathematical precision, but it remains silent about the mechanism that converts potentialities into actualities. This suggests that our most fundamental theory of matter and energy is incomplete in ways that we do not yet understand. Different interpretations of quantum mechanics offer different solutions to the measurement problem, but each interpretation reveals its own limitations and conceptual difficulties. The Copenhagen interpretation abandons the goal of describing reality independently of observation, suggesting that physics can only describe the results of measurements rather than the underlying reality being measured. The many worlds interpretation preserves determinism, but at the cost of postulating an infinite number of parallel realities that can never be directly observed. The de Broglie-Bohm pilot wave theory maintains realism but requires instantaneous non-local influences that seem to violate the spirit, if not the letter of relativity theory. Computational limits present another fundamental barrier to understanding complex systems, even when we know the underlying laws perfectly. The three-body problem in classical mechanics has no general analytical solution, despite the fact that the gravitational interactions between three masses are governed by Newton's simple inverse square law. Weather prediction is limited not just by measurement uncertainties, but by the computational impossibility of tracking the behavior of every molecule in the atmosphere. Protein folding, despite being governed by well-understood quantum mechanical principles, remains computationally intractable for all but the smallest molecules. These computational limits suggest that there may be aspects of reality that are fundamentally incompressible. Phenomena that cannot be understood through simpler models or reduced to more basic principles, even when those principles are known exactly. The behavior of these systems can only be determined by running the full calculation or allowing the system to evolve naturally, making prediction and understanding practically impossible even when the underlying laws are perfectly consistent. The problem of consciousness presents perhaps the ultimate limit to scientific understanding of consistent physical law. Despite enormous advances in neuroscience and cognitive science, we have no clear understanding of how subjective experience emerges from objective physical processes. The hard problem of consciousness, explaining why there is subjective experience at all, rather than just unconscious information processing, seems to lie beyond the reach of current scientific methodology. Some philosophers argue that consciousness represents a fundamental aspect of reality that cannot be reduced to purely physical processes, suggesting that complete understanding of the universe may require incorporating subjective experience as a basic feature rather than an emergent phenomenon. The anthropic principle introduces another kind of limit to scientific explanation by suggesting that some features of the universe may be fundamentally inexplicable through physical law alone. If we live in a multiverse where all possible values of the fundamental constants are realized somewhere, then the particular values we observe may have no deeper explanation than anthropic selection. This would mean that some aspects of reality that appear to require explanation, such as the fine-tuning of physical constants, may actually be irreducible brute facts about our particular cosmic neighborhood. Free will presents a related challenge to our understanding of how consistent physical laws relate to human experience and choice. If the universe is governed by deterministic laws operating according to definite rules, then every human decision seems to be the inevitable result of prior physical causes stretching back to the initial conditions of the universe. Yet our direct experience of making choices seems to contradict this deterministic picture. Some interpretations of quantum mechanics suggest that quantum indeterminacy might provide room for genuine choice, but random events seem no more compatible with free will than determined events. The problem of induction, first highlighted by the philosopher David Hume, reveals a fundamental logical limit to our confidence in the consistency of physical laws. All of our evidence for the consistency of natural law comes from past observations, but we have no logical guarantee that the future will resemble the past. The fact that the laws of physics have remained consistent throughout the observable history of the universe provides no logical proof that they will continue to remain consistent tomorrow. Our belief in the consistency of physical law ultimately rests on an unprovable assumption that nature will continue to behave in the future as it has behaved in the past. Gödel's incompleteness theorems suggest that there may be fundamental limits to mathematical understanding itself. These theorems prove that any mathematical system rich enough to describe arithmetic must contain statements that are true but cannot be proven within the system. If mathematics is the language of physics, then Gödel's theorems suggest that there may be true statements about physical reality that cannot be derived from any finite set of physical laws. This mathematical limitation might translate into fundamental limits on our ability to achieve complete understanding of the universe through scientific investigation. The limits and breakdowns we encounter in our attempt to understand cosmic consistency do not invalidate the remarkable success of physical law in describing the vast majority of natural phenomena. Newton's laws still predict planetary motions with extraordinary precision. Maxwell's equations still describe electromagnetic phenomena perfectly, and quantum mechanics still provides the most accurate predictions in the history of science. But these breakdowns do remind us that our current understanding is incomplete and that there may be aspects of reality that lie forever beyond human comprehension. Perhaps most importantly, these limits suggest that the universe's consistency may be more subtle and complex than our current theories suggest. The breakdowns we encounter may not represent fundamental failures of cosmic law, but rather limitations of our particular mathematical and conceptual frameworks. Future theories that transcend these limitations may reveal new forms of consistency that operate at levels of reality we cannot currently access. The limits and breakdowns of current physics may be pointing us toward deeper truths about the nature of reality that we have yet to discover. After journeying through the vast landscape of scientific discovery, from ancient Greek philosophy to quantum mechanics, from cosmic inflation to black hole physics, from elegant symmetries to fundamental breakdowns, we arrive at the ultimate question that has driven this entire exploration. Why does the universe follow consistent rules? The answer, as we've discovered, is not simple or singular. Instead, it emerges from the convergence of multiple profound insights that, when woven together, reveal something extraordinary about the nature of reality itself. The universe follows consistent rules, not for one reason, but for many interconnected reasons that operate at different levels of reality, from the mathematical structure of existence itself to the quantum foundations of matter and energy, from the symmetries that generate physical law to the anthropic constraints that determine what kinds of universes can contain observers capable of asking this question. The mathematical universe hypothesis provides perhaps the most fundamental answer to our question. According to this perspective, developed most comprehensively by MIT cosmologist Max Tegmark, the universe follows consistent mathematical rules because the universe literally is mathematics. Physical reality isn't made of some mysterious substance that happens to obey mathematical laws. Physical reality is the mathematical relationships themselves, playing out in the arena of space and time. From this viewpoint, asking why the universe follows mathematical rules is like asking why triangles have three sides, or why 2 plus 2 equals 4. The consistency of physical law emerges from the logical consistency of mathematics itself. This mathematical perspective explains why human minds, shaped by evolutionary pressures that had nothing to do with advanced physics, are nevertheless capable of discovering the deep mathematical structures that govern reality. We can understand quantum mechanics and general relativity not because of some miraculous coincidence, but because our cognitive abilities evolved within a universe that is fundamentally mathematical, and our capacity for mathematical reasoning allows us to access the same abstract relationships that constitute physical reality itself. The unreasonable effectiveness of mathematics in the natural sciences becomes perfectly reasonable when we recognize that mathematics and nature are different aspects of the same underlying reality. But the mathematical universe hypothesis, while compelling, must be combined with insights from quantum field theory and the nature of information to provide a complete picture. The universe appears to follow consistent rules because reality itself is a form of information processing, with quantum fields serving as the hardware and physical laws serving as the software that governs how information propagates and transforms throughout spacetime. From this information theoretic perspective, the universe is fundamentally computational, and the consistent rules we observe emerge from the logical constraints that govern how information can be processed and stored in quantum mechanical systems. This computational view of reality helps explain why the universe exhibits both deterministic consistency at macroscopic scales and probabilistic behavior at quantum scales. The apparently random outcomes of quantum measurements aren't truly random, but represent the universe's method of processing information in situations where multiple computational pathways are possible. The collapse of quantum wave functions during measurement represents the universe making definitive computational choices, selecting specific outcomes from the vast space of quantum possibilities. The consistency of physical law emerges from the logical structure of quantum computation itself. Symmetry provides the architectural framework that makes both the mathematical and computational perspectives possible. As Emmy Noether's theorem demonstrated, every continuous symmetry in nature corresponds to a conservation law, and these conservation laws are what create the consistent rules that govern physical processes. The universe follows consistent rules because it is built on a foundation of mathematical symmetries that automatically generate the conservation principles we observe. Space and time themselves possess symmetries that create energy conservation, momentum conservation, and angular momentum conservation. The fundamental forces emerge from more abstract gauge symmetries that ensure the consistent behavior of quantum fields. But symmetries do more than just generate conservation laws. They provide the logical structure that makes physical law possible at all. Without symmetries, there would be no stable patterns, no predictable relationships, no consistent rules that could persist across space and time. Symmetries create islands of stability in the ocean of possibility, defining the mathematical frameworks within which consistent physical processes can operate. The universe follows rules because symmetries create the logical scaffolding that makes rule-following behavior inevitable. The concept of emergence adds another crucial layer to our understanding of cosmic consistency. The consistent rules we observe at macroscopic scales emerge from more fundamental quantum mechanical processes through the mechanism of decoherence and quantum measurement. Classical physics, with its deterministic trajectories and definite properties, emerges from quantum physics through the interaction of quantum systems with their environments. This emergence is not arbitrary or accidental, but follows definite mathematical principles that ensure the consistency of the classical world that emerges from quantum foundations. Similarly, the complex, consistent behaviors we observe in biological systems, ecological networks, and social structures emerge from simpler rules operating at lower levels of organization. The consistency of natural law operates at multiple scales simultaneously, with higher-level consistencies emerging from, but not reducible to, lower-level rules. This hierarchical structure of consistency means that the universe can exhibit stable, predictable behavior at many different levels of organization, from quantum mechanics to cosmology, each level following its own consistent rules while being grounded in the consistency of deeper levels. The anthropic principle provides a crucial constraint on what kinds of consistent rules are possible in a universe that contains observers. Not all mathematically possible universes can support the complex information processing systems we call life and intelligence. The consistent rules we observe may be selected from a much larger space of possibilities by the requirement that they allow for the emergence and persistence of complex structures capable of observation and reasoning. This anthropic selection doesn't explain why any consistent rules exist at all, but it helps explain why the particular rules we observe are so precisely calibrated to allow for complexity and consciousness. In the context of cosmic inflation and the possible multiverse, the anthropic principle becomes even more important. If eternal inflation creates an infinite number of bubble universes with different physical laws, then the consistent rules we observe in our universe may represent just one solution from a vast ensemble of possibilities. We find ourselves in a universe with elegant, consistent rules, not because such rules are inevitable or necessary, but because only universes with suitable rules can produce observers capable of appreciating their elegance and consistency. Yet even within this multiverse context, the question of why consistent rules are possible at all remains profound. Even if our particular set of rules represents just one option among infinitely many, there must still be some meta framework that makes rule-following behavior possible in the first place. The mathematical universe hypothesis suggests that this meta framework is pure mathematics itself, the logical structure that underlies all possible realities and makes consistent rule-following behavior not just possible, but inevitable. The quantum measurement problem adds a fascinating twist to our understanding of cosmic consistency. If consciousness plays a fundamental role in quantum measurement, as some interpretations suggest, then the consistent rules we observe might actually depend on the existence of conscious observers. The universe might follow consistent rules precisely because consciousness has the power to collapse quantum superpositions and select definite outcomes from the quantum realm of possibilities. This would mean that mind and matter are not separate aspects of reality, but intimately connected components of a single system in which consciousness and physical law co-evolve together. The bootstrap principle provides yet another perspective on cosmic consistency. According to this view, the universe follows consistent rules because only self-consistent mathematical structures can exist. Inconsistent universes would contain logical contradictions that would prevent them from maintaining stable existence over time. The consistent rules we observe represent the mathematical requirements for self-consistent reality. The universe bootstraps itself into existence by demanding logical coherence at every level, from the quantum mechanical description of matter and energy to the cosmological description of space and time. Information theory suggests that the universe's consistent rules emerge from the fundamental constraints governing how information can be stored, processed, and transmitted in physical systems. The laws of thermodynamics, which govern energy flow and entropy production, may be special cases of more general principles governing information flow and processing. Black holes, with their precise relationships between area, entropy, and information content, may represent the universe's ultimate information processing systems, revealing deep connections between gravity, quantum mechanics, and computation. The holographic principle, emerging from black hole physics, suggests an even more radical answer to our question. If all the information in any region of space can be encoded on the boundary of that region, then the three-dimensional reality we experience might be a holographic projection of more fundamental two-dimensional information processing occurring on cosmic boundaries. The consistent three-dimensional physics we observe might emerge from consistent two-dimensional information processing, providing a new perspective on how consistent rules can emerge from more fundamental principles. Ultimately, the answer to why the universe follows consistent rules appears to be multifaceted, involving mathematical necessity, quantum mechanical constraints, symmetry principles, emergent complexity, anthropic selection, and information processing requirements. These different aspects are not competing explanations, but complementary perspectives on a single underlying reality that is simultaneously mathematical, quantum mechanical, symmetrical, emergent, observer-dependent, and computational. The universe follows consistent rules because consistency emerges inevitably from the deepest levels of reality itself. Mathematical logic provides the framework. Quantum mechanics provides the mechanism. Symmetries provide the structure. Emergence provides the complexity. Anthropic selection provides the constraints. And information processing provides the dynamics. Together, these principles create a reality where consistent rule-following behavior is not just possible, but necessary, not just observed, but inevitable. Perhaps the most profound insight from our exploration is that the universe's consistency is not separate from the universe itself, but is the universe itself. The rules don't govern reality from outside. They are reality, expressing itself through the mathematical relationships that constitute the deepest level of existence. The question of why the universe follows consistent rules dissolves when we recognize that the universe is consistent rules, playing out the logical implications of mathematical necessity in the theater of space and time. This realization doesn't diminish the wonder and mystery of existence. It deepens it. The fact that mathematical relationships can give rise to stars and planets, to life and consciousness, to love and beauty and scientific understanding, represents perhaps the most extraordinary fact about reality. The universe follows consistent rules because it has no choice. But in having no choice, it creates infinite possibilities for complexity, meaning, and understanding. The ultimate answer to our question is both simple and profound. The universe follows consistent rules because consistency is the deepest feature of reality itself. We observe mathematical order not because some external authority has imposed it on chaos, but because order emerges inevitably from the logical structure of existence itself. The elegant equations of physics don't describe reality. They are reality, expressing the mathematical relationships that constitute the deepest level of what exists. And there you have it, our journey through the deepest question in science and philosophy. From ancient Greek intuitions about cosmic order to modern theories about quantum gravity and multiverses, we've explored how consistency emerges from the very fabric of reality itself. The universe follows rules because it has no choice. And in having no choice, it creates infinite possibilities for wonder, beauty, and understanding. If this exploration has sparked your curiosity about the profound mysteries that surround us every day, make sure to subscribe to The Lazy Cosmos, where we regularly dive deep into the most mind-bending questions about space, time, consciousness, and the nature of reality itself. Hit that notification bell so you never miss our latest cosmic adventures. And let me know in the comments what aspect of cosmic consistency fascinates you most. Until next time, keep looking up and keep wondering. Because in a universe built on mathematical relationships, the most consistent rule of all might be that there's always more to discover.